Okay, so I made an 8-bit 8-function ALU. This is like my fourth time trying to record the video, but the frame rate gets so bad that all the frames get skipped, so I'm probably going to make this short. It's got an 8-bit input here called A, and another 8-bit input here called B. This time I got it right from right to left. And then a 3 to 8 decoder here, which determines the instruction set. It's got an adder, exclusive OR, and NAND, or not exclusive NOR, and NOR. Over here is the decoder. It takes it makes n inputs from log base 2 of n. Sorry, it makes n outputs from log base 2 of n inputs. Each one is mutually exclusive. Hopefully, if you know anything about digital logic, you know how a decoder works. I'll get more to what that has to do with the ALU later. These are the input lines. Red is A, blue is B. I have them go up like this because previously I had made an ALU with everything going horizontally in 2 dimensions rather than building up, and it got really big, and I ran out of memory, and my computer shut down from my computer had a thermal shutdown because it's a piece of crap. So yeah, made everything go up this way. These are ways to boost the signal halfway up the bridge because you can't put repeaters on diagonal blocks. So no matter what the output is, no matter what the decoder is selecting, input always goes into each function. Over here at the first function, the default position is an adder. I didn't build a half adder on the base level here. I just didn't include anything for the carry in. That way I could just make one full adder and then use the wand tool to copy and paste it 7 times. The carry out climbs a little staircase and then goes all the way over here to the carry in, and then once I got the wand tool to work right, I just copied that over and over again. So all the outputs are on these pink lines here. They all go to the same line and go down. Let's talk about the decoder. So the decoder takes 3 inputs, makes 8 outputs. Whichever output is selected is based off of the representation in binary of what you put in. That right there is the most significant bit. This is the least significant bit. So if you make 111, that's 7, for example. We'll choose the 7th selection will be right here. This will be 111. If you make 000, it'll be the 0th selection, which will be right here. So the selected decoder then goes over here. What I made here is a not gate, so that way I could use this torch to send the power all the way up without having to make some kind of complicated staircase. And it also serves as a repeater as well. And what that does is the decoder meets at an AND gate here. So regardless of what the output is here, remember earlier I had said that the input is always being created. If this isn't selected, if the current decoder isn't selected, then the output from this won't make it through to the final bridge. This way, only the output of one function at a time will actually come back to you, and then it's up to you to interpret the results however you want, assuming you know, I'm asking for an adder or I'm asking for an exclusive OR right now. So everything meets over here. What I made over here is an earlier demonstration of an OR gate. Minecraft has what's called an implicit OR gate, which is basically there's one input here, there's no input here, but because just the way how it works, you get an output right here. The problem is there's a lot of feedback that comes this way. Not really a problem with logical gates because you can't send data backwards, but you can get around this by taking a repeater, putting it here, putting another one here, and then doing that. So you get a 1 here and a 0 here, but nothing comes backwards through the repeater. So that's what these right here are. So that way, when data comes out here, nothing goes back that way. Once again, it's not a problem because of the logical gates, you can't send data backwards through them. But that's essentially what this big long line is that everything converges on, is one gigantic OR gate. So if you wanted to draw a schematic like that, you could include the OR gate. Or if you wanted to, you could just draw the decoder, draw the data lines as being the functions right here. It's not really going into the decoder, and then draw this as a big OR gate, and instead of drawing a decoder, you could draw a multiplexer. So once again, everything goes down onto the flat level. These are, once again, ways for me to boost the signal halfway through. Pink lines are outputs. Everything goes along here. Everything goes underground there. Underground is so it doesn't cross the wires here. These orange gates are, once again, not gates, so I can send the power upwards. And these are the outputs, S0 through S7, right? So I've made a little demonstration. I had already computed and then written down the values, so I can tell you in advance what the correct values are. I can promise you all the values you're about to see are correct. You can do them yourself on Wolfram Alpha. There are bitwise functions on there. Anyway, so right now it's in addition mode, so I'm going to add 42 for A, which is 0, 1, 0, 1, 0, 1, and then 0, 0. And then it's very slow because of all the repeaters. And then I'm going to have a 135 for here. So 1, 1, 1, 0, 0, 0, 0, 1. Once again, the 0, 0, 0 instruction is the adder. Right now everything is by default off. So 135 plus 42 is 177. You can look it up yourself. That in binary is 10110001. When we XOR it, which is 001, we get 1010 1101. So then the AND function would be 0, 1, 0. And you can check them by looking down the line if you're not sure which direction is which. So 42 and 135 is 2, because the only bit that they share is the second bit. Okay, so the AND result is 2, because the only bits shared are A1 and B1, which is 2 in binary. Okay, so the NAND gate, which is 0, 1, 1, is going to be the opposite of that. It's just going to be 1, 1, 1, 1, 1, 1, 0, 1. Then the, what are we at, OR? So it's going to be 1, 0, 0. And that's going to be 1, 0, 1, 0, 1, 1, 1, 1. Like so. NOT is a unary operator, so the B value isn't, the B value is ignored, so we're only looking at the ones complement of the A value. So the NOT one is going to be, I think, 101. Yeah, NOT is 101, which is just the opposite of 42, which is 11010101 instead of 001011010. This is how you can represent negative numbers this way. This would be the sign bit, and the ones complement would just be interpreted everything backwards. So this would be negative 42, I think, or maybe negative 41 or negative 43, based on the parity. But this isn't a very good way of representing negative numbers, because it can have two zeros. All ones is 0 and all zeros is 0. So they use 2's complement, which is where you just subtract 2 to the power of the size of the integer. So minus 1. So no, sorry, 2 to the power of the size of the integer. So if you wanted to get the negative complement of a some number, you would just subtract 2 to the 8. So now we're on exclusive NOR, which is 110, which is 01010010. So 01010010. And then finally is the NOR gate, which is going to be 111, which is going to be 01010000.